All right, we're still in unit number 5, working through example number 7, page 12 of your notes. Second to last video, actually, of this particular chapter. And here's the question. A hockey puck traveling at 20 meters per second slides into a surface with a coefficient of sliding friction of 0.4. Letter A, use the work kinetic energy theorem to derive how far the puck will slide before it comes to rest. Begin by drawing a free body diagram. All right, for those of you that have been following the videos or been following along in class, we've done this question. We did it in chapter number 4, on page 17, I think. And we've done it already, and we solved it. I think we solved it using, the big 3. But now we're going to use the work kinetic energy theorem to solve it. And you're going to find out that I think once you figure this out, I think the work kinetic energy theorem is going to be pretty powerful. So let's draw a free body diagram of this puck slowing down, and then we'll finish it out. So here's our puck. We're going to have it encounter a different type of a surface. The coefficient of friction between that surface and the puck is going to be 0.4. We've got the weight coming down, we've got the normal coming up, and then we're going to have friction working against it. No force pushing this way. No force pushing this way. It's already in motion, so no reason to push it that way. It's already in motion. All it's going to do is slide. All it's going to do is come to rest because of this friction right here. So we have work is equal to a change in kinetic energy. And we got FD cosine theta equals change in kinetic energy is 1/2 mv squared minus 1/2 mvo squared. Zoom in a little bit. All right, and then since it comes to rest, the final velocity is 0. That means this whole term drops out. I'm looking to solve for d. So d is then going to equal, I'm going to divide by f and cosine theta. So I get negative mvo squared over 2f cosine theta. And then d is equal to negative. What do we got here? We've got mvo squared, all divided by 2, and then this f. So what's going on with that f? Well, this f is I've lost track. I'm thinking. This is the force that's causing it to come to rest. And yeah, okay, here it is. All right, so this is the frictional force. So there's F. I had kind of a brain fart there for a second. All right, so this is the force that's bringing it to rest, and then we also then would know that we have an equation for friction. 2 and then mu Fn cosine theta. So force of friction is equal to mu Fn. And then we know that the normal force, this particular one, the normal force is going to equal to the weight because the forces are balanced. So I can come over here and I can say d then is equal to negative mvo squared all over 2 mu mg cosine theta. Masses cancel out, which indicates that the mass of the puck is not going to affect how far it travels. And then I think I got enough information I can plug everything in. So I got negative. The speed there is 20 meters per second. I'm going to square it. Divided by 2, divided by 0.4, divided by 9.8 meters per second squared. Cosine of. All right, let's figure this out. This theta came from, where did this theta come from? I'm kind of chasing it backwards. Okay, it came from a work equation. So that means that theta is going to be the angle between this F and that D. So let's go back to this guy. The motion is this way, it's to the right, and the force is to the left. So that's going to be in 180 degrees. So I'm going to come over here and plug in 180 degrees. All right, let's plug it all in and see what we get. So we're going to go 20 squared. All right, now I'm going to, I'll do it right. Negative 20 squared. Make you feel better. Include the negative. Then I'm going to divide by 2, divide by 0.4, divide by 9.8, and then divide by cosine of 180. And there it is, 51. So it'll take 51 meters to bring it to rest. And if you actually go back to chapter number 4 and look that up, it took, I think, about 51 meters as well in chapter number 4. Very good. We did it. All right, part B. How far will the puck slide if it were moving at 3 times the original speed? Well, I'm just going to go grab this equation and let this equation guide my thinking. So d is equal to, because this is an expression for how far it's going to travel. And let's look in here. If I go 3 times the speed, that means that 3 there, when I insert it into the equation, gets squared. So that's really 9 times. So if I multiply this side by 9, I got to multiply this side by 9. So it's going to be 9 times the distance. So 9 times 51. Okay, it's going to give us 459 meters. Next question. How far will the puck slide if it's 3 times more massive? Well, let's use this equation. Notice there's no mass. The mass actually, where are we at? The mass canceled out up here. And when the mass cancels out, that means it'll have no effect. So we can say same distance. That would be 51 meters. I guess if you want to compare it to the original. Okay, the next video is the last one, and that'll be example number 8.